Bury a log and a strip of copper in the same hole. Water it once, then walk away. Within weeks, the wood will start pulling moisture from every direction, swelling like a sponge, and holding it in place even through drought. Bacteria will swarm the rotting wood and begin releasing electrons, actual electrical current, directly into the surrounding soil. The copper will react with the minerals and moisture underground and start generating its own steady voltage. Roots will grow toward it. Nutrients locked in the soil will break free and become available to your plants. And this system will keep running, quietly, invisibly, for years. No batteries, no fertilizer, no electricity bill, nothing to plug in, nothing to buy again. The science behind this has been documented since 1841. An ancient civilization in the Amazon used a version of it to build soils so fertile they are still producing food 2,000 years later without a single chemical input. No one has been able to fully replicate what they did. A centuries-old German farming tradition buried raw logs to create beds that stopped needing water entirely after the second year. A Scottish clockmaker proved that the dirt beneath your feet is a battery, and a Kentucky farmer used buried coils to power electric lights from the ground itself. These are not 4 different tricks. They are 4 pieces of the same secret, a secret that was quietly buried by an industry that profits when soil stays hungry and gardeners stay dependent. Over the next 40 minutes, you are going to see exactly how these pieces fit together, what happens when you stack them in a single garden bed, and why no one in mainstream agriculture has ever told you this was possible. The story starts with a log, not a fancy one, a dead branch, an old fence post, a chunk of firewood you never got around to burning. In Germany and Eastern Europe, farmers have been burying wood under their garden beds for centuries. They call it Hügelkultur, which translates to mound culture. The technique was popularized by an Austrian farmer named Sepp Holzer, who built these beds at alpine elevations, where most people said farming was impossible. But the practice itself is far older. Farmers across Central and Eastern Europe had been doing it for generations, with no name and no manual. Just observation. Bury the wood. Watch what grows. The method is simple. Dig a trench or pile logs on the ground. Stack branches, leaves, and compost on top. Cover the whole thing with soil and plant directly into it. Mounds can be built anywhere from 2 feet to 6 feet high. One important note on wood selection: use untreated hardwoods, fruit trees, maple, oak, birch, or alder. Never use pressure-treated lumber, which contains arsenic and copper compounds that will poison your soil. Avoid painted or stained wood for the same reason. And stay away from black walnut, which releases a chemical called juglone that kills most garden plants. Cedar and redwood break down extremely slowly and can stall the process. Stick with wood that has already started to soften, and you are off to the best start. What happens next is where it gets interesting. The buried wood begins to decompose. As it breaks down, it absorbs water like a sponge. A single buried log can hold several times its own weight in moisture. During dry spells, that stored water wicks back out into the surrounding soil, keeping roots hydrated without a single drop from a hose. The larger the mass of wood, the more water it stores. Experienced gardeners who build these beds tall enough report that they stop needing irrigation entirely after the second year. Think about what that means. A garden bed that waters itself using nothing but stored rainwater released slowly from rotting wood. No drip lines, no timers, no water bill. Just wood and gravity and patience. In drought-prone climates like Southern California, gardeners have adopted the technique in reverse, burying the wood underground instead of mounding it, and the results are the same. The wood holds the water. The plants drink when they need to, but moisture is only the beginning. The decomposition process generates heat. Billions of microorganisms working inside the rotting wood produce thermal energy as a byproduct of digestion. The temperature inside a decomposing hugelkultur bed can run several degrees warmer than the surrounding ground. Planting season arrives weeks earlier on a hugelkultur mound because the soil is warmer at the surface. Frost-sensitive crops survive longer into autumn. The buried wood is not just storing water, it is heating the soil from the inside, creating a microclimate that extends your growing season in both directions without a single watt of artificial energy. As the wood continues to break down over months and years, it feeds an explosion of soil life. Fungi colonize the logs first, sending white mycelial threads through the grain like an underground internet. Bacteria follow, worms arrive, beetles, springtails, and mites set up shop. The rotting wood becomes a habitat, a city for organisms that break down organic matter and convert it in forms that plant roots can absorb directly. The bed gets more fertile every year, not less. A hugelkultur bed built with large logs can keep producing for a decade or more before the wood fully decomposes. And when it does, what remains is deep, dark, crumbly soil that gardeners describe as the best growing medium they have ever worked with. In side-by-side tests, hugelkultur beds have produced more and larger vegetables than traditional raised beds, with less watering and less fertilizer. The wood did the work, but here is what even most hugelkultur gardeners do not realize. That rotting wood is doing something far stranger than holding water and feeding worms, something that was only proven in a university lab 2 years ago. In 2024, a team at Northwestern University published a study on a device they called a dirt-powered fuel cell. It was about the size of a paperback book, and it worked by harvesting electrons released by bacteria as they digested organic material in soil. The same species of bacteria that colonize your buried wood. The same decomposition process that powers every hugelkultur bed ever built. The researchers tested it in wet conditions and dry conditions. It worked in both, and the numbers were remarkable. The fuel cell generated 68 times more power than was needed to run its onboard sensors and transmit data wirelessly. The lead engineer stated that as long as there is organic carbon in the soil for microbes to break down, the fuel cell could potentially last forever. Soil-based microbial fuel cells have actually been around for over a century, the first demonstrated in 1911, but the Northwestern team was the first to make one work reliably in real outdoor conditions. Read that result again. As long as there is organic carbon in the soil. What is a buried log? Organic carbon. What are the bacteria doing when they decompose it? Releasing electrons. What do electrons flowing through a conductive medium create? Electricity. Your buried wood is not just holding water and generating heat, it is also generating electrical current through microbial activity. The soil around a decomposing log is, well, a living battery. And it has been running beneath the feet of every forest on Earth since before humans existed. Nobody packaged it because nobody could sell it. Now travel 5,000 miles south. Deep in the Amazon rainforest, scientists discovered patches of soil so black they look like they have been dyed with ink. The locals call it Terra Preta de Indio, dark earth of the Indians. This soil should not exist. The Amazon's natural ground is thin, acidic, and nutrient-poor. Tropical heat decomposes organic matter so fast that nothing accumulates. Growing crops for more than a season is nearly impossible. Yet here, surrounded by the worst farmland on Earth, are pockets of ground so rich they have been producing harvests for over 2,000 years. The fertile layer runs up to 6.5 feet deep. It contains 3 to 18 times more carbon than the jungle floor around it. Villagers still mine it today and sell it as premium potting soil in Brazilian markets. For decades, scientists argued about whether this was natural or man-made. Then archaeologists found pottery shards, fish bones, and the unmistakable signature of deliberately produced charcoal throughout the soil. Indigenous Amazonians had engineered it on purpose. They took wood, heated it in low-oxygen pits to drive off the volatile oils and produce charcoal. Not ash, charcoal. A stable, porous, carbon-rich solid that we now call biochar. They crushed it, mixed it with kitchen scraps, fish waste, manure, and broken pottery, and worked it into their garden plots over generations. Before these sites were properly documented, most historians flatly denied that the Amazon could support large civilizations. They were looking at the wrong dirt. Here is the shareable detail that will change how you think about charcoal forever. 1 gram of wood-based biochar contains up to 9,000 square feet of internal surface area. That is not a metaphor. That is a measurement. Under a microscope, charcoal looks like a honeycomb of tiny tunnels, chambers, and passageways carved into pure carbon. If you could unfold all the internal surfaces of a single gram and lay them flat, they would cover more floor space than a studio apartment. Those pores create habitat for billions of microorganisms, bacteria, and fungi that break down organic matter and deliver nutrients directly to plant roots in forms they can absorb immediately. The pores hold water in sandy soil that would drain dry in hours and improve aeration in heavy clay that would otherwise suffocate roots. The charcoal buffers soil acidity, raising pH into the range most food crops prefer. But the property that connects everything in this video is electrical. Biochar carries a strong negative surface charge. Its surface is covered in oxygen-containing chemical groups, carboxyl and hydroxyl groups, that give it what soil scientists call a high cation exchange capacity. In plain language, it acts like a magnet for nutrient ions. Positively charged particles, calcium, potassium, ammonium, zinc, and magnesium, are pulled toward the biochar surface and held there instead of washing away in the next rainstorm. Regular soil lets nutrients leach straight through. Biochar catches them and stores them right in the root zone where plants can actually use them. And critically for the system we are building, biochar increases the electrical conductivity of any soil you add it to. Peer-reviewed studies from multiple countries confirm this. Add biochar and the soil conducts electricity better. You are not just amending the ground with nutrients, you are upgrading it into a better electrical medium. That single property is the bridge between ancient charcoal and Victorian copper. And this is where the third buried secret enters the picture. In 1841, a Scottish clockmaker named Alexander Bain took a plate of zinc and a plate of copper, buried them about a yard apart in damp ground, and connected them with a wire. The soil produced roughly 1 volt of steady direct current. Zinc is more reactive than copper. When both metals sit in a medium containing dissolved ions, the zinc begins shedding electrons. Those electrons want to reach the copper. If the 2 plates are connected by a wire above ground, the electrons take the easy path, flowing through the wire and producing usable current. Below ground, the moist soil carries charged ions between the plates to complete the circuit. The soil is not just holding the metals in place, it is an active participant in the reaction. Every dissolved mineral, every trace of salt, every organic acid in the groundwater becomes part of the electrolyte. The wetter the ground, the stronger the current. The more mineral-rich the earth, the longer the battery lasts. Bain used this current to power the world's first electric clock. His British patent number 8763 describes every detail. The device ran for months. No winding, no refilling, no maintenance. Just a quiet current drawn from the chemistry of the ground beneath his feet. Within years, telegraph companies across Britain adopted the same principle. They buried copper and zinc plates beneath relay stations and used the soil as a return conductor for electrical signals. The earth return method slashed the cost of running telegraph wire by cutting the copper needed in half. Stations along the Edinburgh to Glasgow Railway ran on current drawn from the ground. Engineers documented that aligning the plates north to south, following the direction of the Earth's natural telluric currents, boosted output. Driving the zinc plate deeper than the copper increased voltage further. Damp soil worked best. Dry ground killed the current. But when conditions were right, these Earth batteries ran for months unattended. The ground was alive with electricity, and Victorian engineers were quietly using it to connect an empire. But here is the detail that should have launched an agricultural revolution, and never did. Telegraph workers and local farmers noticed that grass growing directly above the buried plates was different. Darker, thicker, taller. Not by a little, obvious enough to spot from a distance. A station master in Yorkshire pointed out a lush green strip running right along a buried return line. The grass on either side was ordinary and pale, but above the copper and zinc, the vegetation looked like it belonged in a different climate. A groundskeeper in Essex joked that the grass knew where the wires were. The pattern repeated across England and Scotland, along muddy embankments and country lanes, wherever the ground carried current between two buried metals. Nobody published a paper. Nobody sent a researcher. Nobody connected the green grass to the buried battery. The observation passed by word of mouth and then quietly disappeared. That silence would last nearly a century. A Kentucky farmer named Stubblefield took the Earth battery further than anyone imagined possible. In 1898, he patented an electrolytic coil of copper and iron wire, wound around an iron core and buried in damp soil. The patent office called it a battery. Stubblefield called it a receiver, insisting the device was intercepting electrical energy already flowing through the ground. He used the current to power arc lamps on his farm that burned 24 hours a day without stopping. His son Bernard testified that the lamps hung in the trees, their coils buried near the roots, and they never went out. The neighbors could see the glow from the road. There were no wires. Stubblefield's farm was miles from the nearest electrical grid. He also used the current to transmit human voice wirelessly through the ground. On Christmas Eve, 1901, a group of children at his home heard Santa Claus speaking through a receiver with no wires and no conventional power source. Think about what year that was. Marconi would not send a simple click across the Atlantic until December of the same year. Stubblefield was already transmitting clear human speech. 1,000 residents of Murray, Kentucky witnessed a public demonstration on the town square. He showed it in Washington, D.C. on the Potomac River, transmitting from a moving steamboat to shore. Newspapers ran the story nationwide. Then Stubblefield retreated into paranoia, refused to commercialize, and in 1928 was found starved to death in a shack surrounded by his buried coils. His patent is still on file. The coil design still produces current. The man who proved it was erased from history. So now you have 3 technologies, each discovered independently, each documented, each buried. Wood that holds water, generates heat, and feeds a living electrical current through microbial decomposition. Charcoal that rewires soil chemistry, attracts and holds nutrients with an electrical charge, and persists for centuries without breaking down. Copper and zinc that create a steady galvanic voltage, mobilize locked nutrients through electrolysis, and draw roots toward the current through a documented biological response called electrotropism. 3 systems, 3 forms of energy, all buried, all free. And here is the critical insight. They are not just compatible, they are synergistic. Each one makes the other 2 work better. Biochar increases soil electrical conductivity, which strengthens the galvanic reaction. The galvanic current mobilizes nutrients, which the biochar catches and holds. Decomposing wood feeds organic carbon to the microbes that generate biological electricity. Gives those microbes a permanent home. Water stored by the wood keeps the soil moist, which keeps the galvanic cell and the microbial fuel cell running. Remove any one piece, and the system works. Combine all 3, and you get something that compounds over time instead of depleting. The timeline tells the story. Fritz Haber and Karl Bosch cracked industrial ammonia production in 1909. By 1913, the first plant was running in Germany. What had once required years of crop rotation or tons of manure could now be delivered in a bag of white crystals. American farmers spent $300 million on synthetic fertilizer in 1945. By 1975, that number passed $3 billion, a tenfold increase in one generation. The business model was elegant and brutal. Fertilizer runs out. You buy more next spring, every acre, every season, another invoice. A permanent solution buried in the ground, a one-time cost with no recurring revenue, had no place in that economy. It was not that earth batteries and biochar were disproven. It was that they were made economically irrelevant by a system designed around repeat purchase, and the paper trail proves it. The British Electroculture Committee, established under the Ministry of Agriculture in 1918, spent nearly 2 decades collecting field data. Their reports documented substantial yield gains from electrical methods. Physicists, biologists, electrical engineers, and Nobel laureates sat on the committee. Their credentials were impeccable. Then in 1936, the same year industrial fertilizer swept across Europe, every report was stamped not for publication and sealed in government archives. Only 2 copies are known to have survived. The committee was dissolved without explanation. Academic citations for earth battery and electroculture research dropped over 90% in the following decades, the exact period when fertilizer revenue was smashing records. One curve rising, the other collapsing. No secret memo was needed. The market rewarded the disposable, not the durable, but the soil did not forget. Terra preta sites created before European contact are still fertile today with zero synthetic input. A 10-year field study published this year confirmed that a single application of biochar continued to improve soil pH, carbon content, and nutrient availability a full decade after application. The effects did not fade. They compounded. In China, the Chinese Academy of Agricultural Sciences ran a trial across 3,600 hectares, an area larger than 6,000 football fields, using electrical stimulation on crops. Yields climbed nearly 30%. Pesticide use dropped by as much as 70 to 100%, and hugelkultur beds built with large logs continue producing for 10 years or more, the wood releasing water and nutrients the entire time, the microbial community growing richer and more diverse each season. The 3 systems work. They have always worked. The only thing that changed was who was paying attention and who was paying for the research. Now here is the practical part, the part where you stop watching and start building. I'm going to give you 3 methods, simple to advanced. Each one works alone. Combined, they create something none of them can do separately. Method 1. The buried wood bed. Find dead logs, branches, or untreated lumber. Dig a trench about 2 feet deep. Lay the largest logs on the bottom. Stack smaller branches on top. Add a layer of leaves, grass clippings, or kitchen scraps for nitrogen. Cover with at least 6 inches of soil and plant directly into it. Water well the first season. After that, the wood does the watering for you. It will absorb rain, hold it, and release it to your roots during dry spells. The decomposition process feeds the soil biology and warms the bed from within. 1 installation. No maintenance, no irrigation after year 2. Method 2. The charcoal layer. Take clean hardwood charcoal, not the kind soaked in lighter fluid from the hardware store, and crush it to pea gravel size. You can buy lump hardwood charcoal at most grocery stores, or if you want to make your own, the safest backyard method is a top-lit updraft burn in a steel drum with holes drilled near the bottom for airflow. Always do this outdoors in a clear area away from structures, never in an enclosed space, and keep water nearby. Let it cool completely before handling. Before burying any biochar, you must charge it. Fresh charcoal is chemically hungry. Its massive surface area will initially absorb nutrients from surrounding soil, temporarily starving your plants. Soak the crushed charcoal in compost tea, worm castings, diluted fish emulsion, or diluted urine, 1 part urine to 10 parts water for at least 48 hours. This loads the pores with nutrients and beneficial microbes, so the biochar starts giving instead of taking. Then work it into the top 6 to 8 inches of your bed at 10 to 15% by volume. The charcoal increases electrical conductivity, holds nutrients in the root zone, buffers pH, and provides permanent housing for beneficial microbes, it will not decompose. It will still be there in 100 years, still holding charge, still attracting nutrients, still hosting life. Method 3. The copper-zinc earth battery. Take a 6-inch piece of copper pipe and a single galvanized nail. 1 pair per plant is the limit. More is not better. Too much zinc will accumulate in the soil and stress your plants, and excess copper can harm earthworms and beneficial microbes. Push the copper into the soil on one side of your plant and the zinc nail on the other, about 8 to 12 inches apart and 6 inches deep. Moisture completes the galvanic circuit. A multimeter should read between 0.8 to 1.1 volts. The current mobilizes nutrients locked in chemical bonds through a process called electrolysis. Roots grow toward the copper through electrotropism. The zinc slowly corrodes and releases zinc ions, which plants need to produce auxin, the master growth hormone. Without zinc, plants cannot manufacture tryptophan, the amino acid at the heart of auxin synthesis. The zinc is not wasted. It is consumed by the very biology it powers. When the zinc nail is visibly corroded and your voltage drops below half a volt, swap in a fresh one. The copper side usually lasts several seasons. Now combine them. This is the part nobody else is showing you. This is the 3-layer system. Think of it as building a living machine underground. Layer 1, the foundation. Dig your trench 2 feet deep. Lay the largest logs and branches on the bottom, the same untreated hardwoods we talked about earlier. Pack smaller sticks and wood chips into the gaps. This is your water reservoir, your heat engine, and your microbial fuel cell. As the wood rots over the coming years, it will absorb thousands of gallons of rainwater and release it slowly. The microbial decomposition will generate heat from below and produce a continuous trickle of biological electricity as bacteria release electrons. Layer 2, the charcoal zone. On top of the wood, spread a thick layer of charged biochar mixed with compost, 4 to 6 inches deep. This is your nutrient magnet, your electrical conductor, and your permanent microbial habitat. The charcoal will not decompose. It will outlast the wood, the copper, and probably the fence around your property. Its 9,000 square feet of surface area per gram will catch every nutrient ion that the decomposing wood releases and hold it in the root zone instead of letting it leach into the water table. Its electrical conductivity will bridge the gap between the biological current from below and the galvanic current you are about to install. Layer 3, the root zone. Cover the charcoal layer with 6 to 8 inches of your best garden soil. This is where you plant. Press 1 copper pipe into one side of the root zone and 1 galvanized zinc nail into the other, about 8 to 12 inches apart and 6 inches deep. Remember, 1 pair per plant. Do not overdo the metals. The biochar-enriched soil between them is a superior electrolyte compared to plain dirt. More ions, better conductivity, lower resistance. The galvanic reaction runs stronger and lasts longer. Nutrients mobilized by the electrical current are immediately caught by the surrounding biochar. Roots grow toward the copper through electrotropism, entering the most nutrient-dense zone in the entire bed. The zinc slowly releases ions that plants need for auxin production, the hormone that drives stem elongation, fruit development, and root branching. Without zinc, plants cannot manufacture tryptophan. Without tryptophan, there is no auxin. Without auxin, growth stalls. The zinc electrode is not wasted. It is consumed by the very biology it powers, atom by atom, season by season. Every layer feeds the others. Wood powers the biology from below. Charcoal holds the chemistry in place. Copper and zinc drive galvanic electricity through the root zone. Water is stored in the logs and released on demand. Heat radiates upward from the decomposition zone. Nutrients cycle in a closed loop, but nothing leaves. Everything compounds. Track your results. This is what separates experimentation from wishful thinking. Buy an inexpensive refractometer and measure Brix readings on your plant leaves every 2 weeks. Brix measures dissolved sugars and solids, a direct indicator of plant health and nutrient density. Higher Brix numbers mean a healthier, more nutritious plant that is also more resistant to pests. Some electroculture practitioners report Brix increases of 2 to 3 points within a single month. Take voltage readings with a digital multimeter by pressing one probe to the copper and one to the zinc. You should see a reading between 0.8 and 1.1 volts. If it drops below 0.5 volts, the zinc may need replacing. Photograph your plants beside a ruler every week. Weigh your harvest at the end of the season on a kitchen scale. And critically, run a control row with no wood, no charcoal, and no metals. Same soil, same water, same sunlight, same seeds. Let the numbers tell the story. Document everything. This is how backyard observations become repeatable science. This is how we rebuild the evidence base that was sealed in a vault 90 years ago. There is one final detail that makes this system unlike anything else in agriculture. Terra preta soils in the Amazon have not just persisted for 2,000 years, they have grown. Scientists confirm that biochar creates such a favorable environment for microorganisms that the microbial community continually pulls new organic material into the soil matrix. Fresh leaves fall, microbes colonize them, break them down, and incorporate the carbon into the existing biochar structure. The soil builds itself. It gets more fertile every year without human intervention. That is the opposite of every farming system used today, where each harvest depletes the ground and demands another purchase. And when you add buried wood beneath the charcoal, you are feeding the system from below at the same time nature feeds it from above. Carbon enters from two directions. Electricity is generated by both galvanic chemistry and microbial metabolism at the same time. Water is stored, heated, and released by the wood. Nutrients are attracted, held, and delivered by the charcoal. It becomes a closed loop, a living engine. There is a larger picture here too. When you bury charcoal, you are locking carbon into the ground for centuries. The trees that became that charcoal pulled carbon dioxide from the atmosphere through photosynthesis. Pyrolysis converts it into a form so stable it resists decomposition for thousands of years. Every handful of biochar you bury is atmospheric carbon permanently removed and stored underground. The ancient Amazonians were not just feeding their families. They were running the oldest carbon capture program on Earth, and it worked. The proof is still in the ground. The three-layer system does the same thing. It feeds your garden and buries carbon at the same time. But infinite energy is not a marketing phrase. It is a description of what soil does when you give it the right materials and then get out of the way. Wood decomposes and produces biological electricity and heat for a decade. Charcoal holds charge and hosts microbes for centuries. Copper and zinc produce galvanic current for years. And the whole system regenerates itself through microbial activity, pulling in new organic carbon from the surface, growing richer and deeper with every passing season. No battery runs forever, but a system that rebuilds itself from freely available inputs, rain, fallen leaves, and the chemistry of the ground comes as close to forever as anything in nature can. The fertilizer industry is worth over $200 billion a year. The pesticide market adds $60 billion more. Both depend on you coming back every season with your wallet open. A buried log costs nothing. It is probably sitting in your yard right now. A bag of hardwood charcoal costs $4. A copper pipe costs $3. A galvanized nail costs pennies. One installation that feeds itself, waters itself, heats itself, generates its own electricity, and gets stronger every single year it sits in the ground. The reason this is not taught in every agriculture program on Earth is not that it does not work. It is that it works too well and too permanently for an economic system built on annual depletion and repeat purchase. The charcoal that ancient Amazonians buried before the Roman Empire existed is still in the ground today, still producing food with no fertilizer and no maintenance. Hugelkultur beds built a decade ago are still moist and fertile without irrigation. Bain's earth battery still produces voltage. Stubblefield's coil still generates current. The physics, the chemistry, and the biology have never changed. The patents are on file. The soils are still in the ground. The only thing that changed was who controlled the conversation about how food should be grown. The experiment cost less than $10 total. The buried log is free. The charcoal is pocket change. The copper and zinc are hardware store scraps. The science has been documented for nearly 2 centuries. The proof has been growing in the Amazon for 2 millennia. The only variable left is you. If this changed how you think about what a handful of dirt can do, send it to someone who grows things. The best way to unbury a forgotten science is to plant it in every garden on the street. If you want more stories like this, hit subscribe. There is a lot more buried out there, waiting to be found.